When an advanced data warehouse is built on the same rigid geometric principles as a transactional database, the structure begins to buckle under analytical pressure. This happens because the third normal form, the logic used to ensure precision in a banking system, creates a massive mechanical conflict when applied to a warehouse. The design rules that prevent data corruption during an ATM withdrawal will actively grind a million-row analytical query to a halt. To score full marks on this architecture, a student has to recognize exactly where the standard rules of relational design stop being an asset and start becoming a bottleneck. Solving this requires a specific shift in strategy, introducing deliberate, calculated data redundancy to prioritize read speed over storage efficiency. Engineering at this volume isn't just about managing more data. It requires a structural departure from the transactional reflexes we're taught first. A standard OLTP workload consists of frequent, single-row operations. Think of a retail database processing thousands of individual credit card swipes per minute. These systems rely on third normal form to isolate every data point. This ensures that if you update a customer's address in one table, it doesn't create a conflict in 5 others. Analytical workloads, or OLAP, follow WH-Inmann's criteria. They are defined as being non-volatile and time-variant. Unlike a production database, once data is loaded into an OLAP warehouse, it is permanently locked. It becomes a read-only historical record. The user behavior shifts from writing a single row to running aggregates, like sums and averages, across 10 million rows at once to identify seasonal trends. An architecture optimized to safely write one row at a time cannot physically scale to read 10 million rows simultaneously. This diagram illustrates the computational friction inherent in the SQL join operation when it's forced to work at scale. To calculate something as simple as quarterly sales, the database must spider out and mathematically link the customer, product, and store tables together. Executing these multiple joins across a dataset of millions of records creates a performance penalty that grows exponentially. The resulting spike in CPU and memory usage often causes the system to time out before finishing. Now, contrast that processing delay with the expectations of a modern analytical environment. An executive using a business intelligence dashboard expects near-instant load times, not a query that takes several minutes to resolve. In this context, the normalized SQL join is the primary obstacle to performance. The core challenge of OLAP engineering is removing that join bottleneck to restore query speed. This is the star schema. It is a dimensional model designed to bypass the traditional join bottleneck by simplifying the data's physical layout. At the center is the fact table. This is the repository for quantitative metrics, the numbers like units sold and total revenue. To navigate these numbers, the fact table uses a composite primary key made up entirely of foreign keys. These keys connect to the surrounding dimension tables, which hold the descriptive attributes used to filter and group those central metrics. This architecture ensures that every query is only a single hop away from the data it needs. By design, the star schema transforms a complex web of relations into a direct access radius. If we look inside a single dimension table, we can see exactly why the system is faster. This table is full of redundant, repeating text strings. That's because the database architect has intentionally denormalized the data. This approach is a direct violation of the third normal form. But by pre-flattening the data, we remove the need for the database to perform secondary table lookups at runtime. This is a matter of economics. Physical storage space is currently cheap and abundant. Computational read performance, however, is expensive and finite. Saving a single join operation during an analytical scan is worth the cost of storing thousands of duplicate strings. In a data warehouse, deliberate redundancy is the price we pay for speed. However, there are cases where physical storage is a strict constraint, and that redundancy becomes too expensive to maintain. This is the snowflake schema. It's a variant of the star model that reintroduces third normal form back into the dimension tables. By normalizing these dimensions, we strip away the duplicate strings. Those repeating categories are moved into independent lookup tables, linked by new foreign keys. This successfully eliminates storage waste and data duplication, but it comes with a cost. Pulling that same report now requires additional join operations to traverse the new subtables. The Snowflake schema solves the storage problem, but it does so by compromising the primary objective, query speed. When evaluating these two schemas, we have to look at the specific trade-offs involved. On normalization, the star schema is denormalized. It intentionally preserves repeating strings. On performance, the star schema has minimal join overhead, leading to the fastest possible read speeds. Conversely, the Snowflake schema is strictly normalized to third normal form. This results in high join overhead and significantly slower read performance. The choice between them depends entirely on whether the priority is the executive's dashboard speed or the cloud storage budget. Mastering this architecture means recognizing that every structural choice is a calculated compromise. The rigid rules of relational databases that are taught in traditional textbooks simply do not apply universally when dealing with analytical data. Applying transactional normalization to an analytical system is a design error that ensures a performance bottleneck. To architect a high-performance data warehouse, an engineer must leave the third normal form behind.